This is the gas behavior playlist on Catalyst University. My name is Kevin Tokoph. Make sure to like this video and subscribe to the channel for future videos and notifications. In this video, we're going to introduce something called kinetic molecular theory, and we're going to use this theory and several assumptions to actually derive ideal gas behavior and the expression that describes it, which we know is either written as PV equals nRT, or the actual form that comes out of the derivation is P equals nRT over V. What is kinetic molecular theory, which I abbreviate here KMT? Well, it has to do with ideal gas behavior. Real gas behavior is not described like this because we have three very important assumptions that go into this theory and the subsequent derivation. First of all the gas particles in a container, so you can see one particle right here in a square container, but they don't interact. There are no intermolecular forces between the various molecules or particles in the gas. So for example, do we account for hydrogen bonding? No, we assume there's no hydrogen bonding. We assume there's no van der Waals attractions. We assume that there's no dipole-dipole interactions. Any attractive or repulsive force is not accounted for in this model. They don't exist, okay? So basically every particle behaves as if no other particle is present. Okay, that's the first assumption. The second assumption is that the particles are point masses. What that basically means is they have mass. It's just the mass of whatever the molecule is. If we got a molecule of water, it has a mass of 18 grams per mole. Okay, but that molecule or that atom, whatever it is, does not occupy any volume. It has zero volume. So that means a particle, in addition to not interacting with another particle, it basically can move directly through another particle because it occupies no volume. There's no collisions between molecules, really, because they're point masses. They have no volume, so they can just go around the container as if no other particle is present. So they have their mass, but absolutely no volume. And the other thing, which is sometimes stated in different ways, is that all the kinetic energy is conserved with each collision. So the particles will collide with the walls of the container, and they will consequently change direction and momentum, okay? But all the kinetic energy is conserved. So that means all the collisions are 100% elastic. So when a particle collides with a container with some momentum, it will simply change direction and not the magnitude of the momentum. Okay, so all the collisions are elastic. That also implies that something which is usually not talked about, but in case it crops up, the coefficient of restitution for every collision is 1, which implies that all the collisions are 100% elastic. Okay, now these are the three main assumptions that you need to understand. There are also some limitations of kinetic molecular theory, and it's really just that it fails particularly when you have low temperature, when there's high pressure or low volume. So in real situations, if you have a gas that has high temperature, there's low pressure, and a very high volume, that tends to be conditions where you might be able to use ideal gas behavior, and these assumptions would not fail too badly. The other thing about this is that the ideal gas equation does not predict real gas behavior. There are some situations, like I've mentioned here, low temperature, high pressure, low volume, where the behavior deviates pretty far from ideality. And so what we have to do is invent other equations, which we'll introduce in later videos, which are real gas equations of state. And examples of that you've probably heard of from general chemistry might be the van der Waals gas, or van der Waals equation of state. And there's actually several others, and which one you choose depends on the conditions. And we'll also see later on we're going to invent another physical parameter called fugacity. It's basically a substitution for pressure that accounts for real behavior. And sometimes you may choose to use this instead. We'll talk about that in later videos. But that's enough on the assumptions and limitations of kinetic molecular theory. Let's actually use the theory to show the derivation of the ideal gas equation of state. All right, so first of all, we need to define two things first. So first of all, we have a particle here in a box, okay? It's in a container, and let's suppose we're only considering the x direction. We could, in theory, consider the y and z directions, but that makes the calculation and derivation much more complicated, and you would end up getting the same answer as you do with only accounting for one direction. So we're going to talk about the x direction. And we've got a particle here of mass m moving with a velocity vx. Okay, so it's velocity in the x direction. Recall that mass times velocity is the momentum at a given point in time. Okay, so we've got a particle, it's moving directly orthogonal to this wall of the container, and when it hits the container, as you see right here, it's going to bounce back at the exact same speed but in the opposite direction. And since the velocity is in the opposite direction now, but of the same magnitude, the momentum is also of the same magnitude, but now it's in the opposite direction. Okay? Hopefully that makes sense. We can actually quantify what that change in momentum is. So recall that a change in momentum, which is given by P, is P2 minus P1, or P final minus P initial, however you want to talk about it. And I mentioned that a given momenta at any point in time is the mass times the velocity at that point in time. So P2 minus P1 can be written as mv2 minus mv1. Okay, now here's where I kind of intentionally mixed up the signs here, because normally we do final minus initial. The final in this case is a negative, so technically this should be, if we're accounting for the particular velocities at these given points, mv2 minus mv1 should be negative mvx minus positive mvx. And so your overall change in momentum should be negative 2 mvx. All right, it really does, the sign here doesn't matter. Okay, I'm choosing to actually put the initial one first, so mvx minus a negative mvx, so that the overall result ends up being positive. It just, negative signs make it a little more confusing. It really doesn't matter. Okay, the point is the total change in momentum has a magnitude 2 times the mass times the velocity in the x direction. This is the change in momentum per one particle. Okay, just this orange particle right here. What if I wanted to account for the entire change in momentum of every single particle in this container? So there's millions of other particles. Well, the total change in momentum is equal to the change in momentum per collision. Okay, so here's one collision right here. We just calculated that that is 2 mvx. So that's actually what this will end up being right here. Change in momentum per one collision times the total number of collisions. Okay? And these are two important things we're going to take to the next slide. All right, here's where it gets hairy, but just see if you can follow. I've just pasted these up here. That's what we just did on the previous slide. Now here's some important things. A change in volume. Remember, volume is the length times the width times the height. Well, in a different order, it's the dw, differential of width, times the change in height times the change in length. All right, and length I'm choosing to make the x direction. Now this width times the height, that could be the area, so a differential volume is equal to differential A times differential length, or x. Okay, and I could equally write that as A dx, because I'm not changing the area. There's no compressions, no expansions, the area is going to be constant here at this point in time. So dv equals A dx. Now recall that dx, or just position in general, is equal to the product of velocity times the time. So I can write this dx as v dt. Therefore, dv, the volume that is equal to A times v dt. In other words, differential volume is equal to area times the velocity dt. Okay? Keep this in mind. Now, we also want to be able to determine the total number of collisions. So this number of collisions right here is going to be this n, big N, collisions, the number of collisions total. Well, I first have this concentration term. Why is it concentration? Well, I have moles on the top times n sub A. This is Avogadro's number. Usually you don't see it written like this in general chemistry, but in physical chemistry, a lot of times Avogadro's number is written as capital N with a subscript A. So if you take moles times the Avogadro's number, this numerator would be the total number of molecules. And then if I divide the number of molecules by the volume of the container, that gets me an effective concentration, the number of molecules per unit volume. So if I take the number of molecules per unit volume and multiply by the total volume, that should get me the total number of collisions, right? So I can put a volume term here, but volume is just equal to A times the velocity in the x direction dt, or delta t as we'll put it in a little bit. And why is there a 1/2 multiplied by this whole term? Well, remember that we're only considering the x direction, and theoretically half of the molecules are moving towards the right, the other half are going to be moving towards the left. And we're only considering the particles hitting this right wall. Okay, so it's only going to be half of them. The other half are going to be hitting the left wall. So that's why there's a 1/2 multiplied by that. Okay? Now, from here, what is our total change in momentum? Well, we already determined what the change in momentum was per collision. That was 2 mvx. That goes right here. Then, the total number of collisions is this n subcollisions. So we're just going to put this whole thing right here. All right? Now notice several things. One, we have a 2 out in front, and at the end we have a 1/2. So 2 times a half is just 1, so those end up canceling out. Also notice we've got this velocity right here, and we've got another velocity right here. So what I'm going to do is I'm going to throw these in together and make this the root mean square of the velocity. Okay? So when you see these little weird brackets, usually around a term that's squared, that means it's the root mean square of that particular variable. Okay, so the mass times the root mean square of the velocity, and then I'm still left with this concentration term times the area times, now I'm going to change it to delta t, although it really doesn't matter, times the time interval. Okay? Now, I'm going to divide through both sides by this delta t. So when I do that, I get what's down here, the total change in momentum over the total time interval. So delta p over delta t. All right? And then I have all this stuff. Mass times the root mean square of the velocity times the concentration term times the area. Now, an aside here from fluid physics, the pressure is equal to the force exerted on a specific area over the area over which that force is exerted. So pressure equals force divided by area. Also, from Newton's second law, force is equal to mass times the acceleration at a given point in time. So force over area is ma over big A, which is the area. Now let me factor out m over a. So mass over the area is multiplied by the acceleration, which is the same thing as the first derivative of velocity with respect to time. All right? But what I want to do is now throw this m inside the differential. So instead of just having dv, now I'm going to have d mv over dt, and I still have this 1 over area multiplied out in front. Now the reason I do this is because, first of all, mass is not changing, so technically mass is a constant, so it doesn't matter if I put it inside the differential or leave it outside. But by having a differential mv, that's the same as differential p. So the pressure is equal to 1 over the area times the derivative of momentum with respect to time. And I'm going to go ahead and change this differential notation into delta notation. So dp dt I'm going to replace as delta p over delta t, still with the 1 over area multiplied out in front. And that expression is the pressure. Now, we just found an expression for delta p delta t right here. Let's substitute all this stuff in. So my pressure is equal to 1 over the area times what I just substituted in, mass times the root mean square of the velocity from up here, times the concentration term times the area. All right? Now, a couple things happen. One, I have 1 over area here, and I have an area right here, so those cancel. So then I get down to this, which I now have copied and pasted up here. Now, one substitution. Mass times the root mean square of the velocity, this turns out to be equal to Boltzmann's constant times the temperature. So I can now make that substitution by this term out in front. So the pressure is equal to Boltzmann's constant, K sub B, times T, times this concentration term. Now, I actually have two constants here. The first one is Boltzmann's constant, that's obviously a constant. And then I have Avogadro's number, which is big N sub A, which we know is 6.022 times 10 to the 23rd molecules per mole. Well, if I have Boltzmann's constant, which is a constant, and I multiply it times Avogadro's number, which is also a constant, the product of two constants is also a constant. And the product of these two constants we're going to define as another constant called R. And R is going to be what you probably expect it to be, the ideal gas constant. And then we're going to go ahead and make the substitution in for KBNA. So first I'm going to group those two together. So I have N the number of moles, in parentheses now, Boltzmann's constant times Avogadro's number, and then times temperature divided by volume. And finally I'm going to make that last substitution, and I get one form of the ideal gas equation. It says the pressure is equal to nRT over V. And there you have it. This is the ideal gas equation, and that is how it's derived. And pretty much what you see here is it's derived pretty much using two things. One, kinetic molecular theory, which is very important. It has all of these assumptions that we talked about at the very beginning of this video, but it's also derived simply from Newtonian mechanics. Okay, that's all you really need. All we had here was pretty much momentum. We had basic geometry, volume, area, so on and so forth, and pressure and force. That's really all we had, just Newton's laws, Newtonian mechanics. Able to combine those two things together, and we derive the ideal gas equation of state. All right? So there you have it. So hopefully this made sense where this equation comes from. All right? Now, in the next few videos, we're actually going to do some practice problems, some basic review of some of the things you can do with the ideal gas equation of state. But after that, we're actually going to then go into real gas behavior, and we're going to find different ways to quantify that. All right? So please make sure to like this video and subscribe to the channel for future videos and notifications. Thank you.